The following presentation was recorded at the 2025 Southeast Linuxfest in Charlotte, North Carolina. It is licensed under a Creative Commons license. For more information on the Southeast Linuxfest, visit www.southeastlinuxfest.org. Come join us next June.
Welcome to the Roots of Linux. And I'm sitting down because I'm old and going to try to speak loud enough, and hopefully we're not going to get too much crosstalk from on the other adjacents. I was Multics systems administrator from 1978 to 81, Unix at various kinds, and been a Linux user since 1995. I'm not going to read everything on the slides, so those of you that can see the screens, you're going to get a little more information than those that don't. Now, come on. It's supposed to advance when I click the, what is Linux? Well, Linux is a Unix clone created by Linus in 1991. And that 22 years distance from the beginning of Unix, which was 1969 to 1991, resulted in a lot of changes in Unix between what it started out and what it was when Linus created Linux. And he first implemented it on the Intel 8386 or i386, a computer chip that implemented paged segmented memory, which is what one of these things. And what fascinated Linux as much as anything was the fact that he had a paged memory environment that was, a virtual memory environment that was affordable to a college student. And it is a clone that, at least officially, there are no Unix code in Linux. And it implements the POSIX standard. There was what called the Unix wars at this time. Different manufacturers had licensed Unix, and they were trying the Roach Motel. You can check in, but you can't check out. They were trying to lock the users into their Unix environment. And the customers, the users, did not like that. They didn't want to be locked into IBM, AIX, or PowerPC, or Hewlett-Packard, or digital equipment, whatever hardware. They wanted, one of the advantages of Unix was portability. They wanted to be able to write software and run it anywhere. And this POSIX standard API and features required for made a portable Unix environment at least practical. And of course, the usual thing about it's a kernel only, and there's distros with different user lands, mostly GNU, but about everything that you could possibly use has been tried at least once. So Unix is important because it's the ancestor of most modern operating systems and Linux. And what were the roots of Unix? Not Linux, but Unix. Unix being a root of Linux, is based on primarily two things: Multics and the compatible time-sharing system. Despite what you may read in the textbooks, it's mostly based, or at least the initial version, was based on compatible time-sharing system, which you've probably never heard of, but it was. We'll talk about that more. Ken Thompson and Denis Ritchie worked on the Multics operating system at Bell Labs, which was one of the partners of developing the Multics operating system. And the development environment was compatible time-sharing system, which at that time was probably the best programming development environment that existed. And here's a quote from Denis Ritchie, and I'm not going to give the reference, but in most ways, Unix was a very conservative system. Only a handful of ideas are genuinely new. In fact, a good case can be made that is, in essence, a modern implementation of MIT's compatible time-sharing system. And that was made in 1978. Things changed between the modern day and the present day and then, but a lot more features have been added. Some from Multics and some original in the Unix, and the compatible time sharing system was a part of Project Mac at MIT, and it was implemented on the IBM 79Xs. First, the 709 was the test base, and then the 7090, and then the 7094. So they made a test run in 1961, got a lot of government ARPA, not DARPA at the time, just ARPA money, Advanced Project Research Agency. And the project was joined by GE, we'll see, and BTL, Bell Telephone Labs, AT&T Bell Telephone Labs, which was one of the finest research outfits in the country at the time. They invented the transistor. They did a lot of computer research, and it's a shame that they pretty much ceased to exist. And Multics was a follow-on, basically, to CTSS, Compatible Time Sharing System. And I'll go on. It was one of the first time-sharing systems, and it allowed interactive terminals, 110 baud ASCII teletypes, mostly. They could also connect into the teletype network, which was in North America, some in Central and South America. So you had dial-up slower speed circuits that you could dial up and essentially access Multics throughout North America and some in South America and so on. But most of the users were in MIT or the New England area, because the New England colleges used MIT's compatible time sharing system. And well, significant influence on Unix, yes. As we've already seen, Denis Ritchie basically said, they re-implemented a compatible time sharing system on the hardware they had because basically they wanted a good debugging and programming environment. The IBM 709 was used for the first test in 1961. It's an improved 704. The 704 was where Fortran was first implemented and Lisp was first implemented. It had a whopping 32K 36-bit words. You could say that it's maybe 140K bytes, accounting for the 36-bit words. And that was a big amount of storage. I mean, it was the first times that you could do that. And it had double precision floating point. It was a vacuum tube machine, but it had some transistors in the memory unit. And what they used in the production, once they got the ARPA money, was an IBM 79, which was faster and cheaper than the 709. And this was in the era that the next machine was significantly faster, just like we had in the microprocessor era for a while. Yeah, the rough number of transistors in the 7090 was about the same as that as this thing, the Intel 8386. It did have the 7090 had channels in it, which were essentially microcomputers that could also directly talk to peripherals and move data in and out. So it had a lot more I/O power than perhaps the 8386 did, but it was not terribly more faster. They did do a little, magic in designing it. It was at the point where they started to understand pipelining and so on, but it wasn't quite, it wasn't a heavily pipelined machine. And it was the 7090 significantly faster, half the rental price. And the compatible time sharing system was developed at MIT under Project Mac, and it was compatible with, from this point of view, it was compatible with the Fortran monitoring system, which was a very primitive operating system. It was basically a operating system that enabled batch processing of Fortran off of punch cards and output to paper tape, which was then printed out on, paper tape, magnetic tape, which was then printed out on the line printers. And I'll just mention that at this time, or shortly after, there was a lot of interest in time sharing. These are a few of them that were done. There's another one that was quite interesting, done at MIT. It was called ITS, which was the incompatible time sharing system. It was done on a DEC PDP-10 by the Artificial Intelligence Lab, and they just had a perverse sense of humor. But the name wouldn't mean anything if you didn't know about the compatible time sharing system. Compatible time sharing system had a impact on operating system design, and it also had it probably had the first electronic email. It was just among the roughly 600 users that they had it, not simultaneous users, but the total group of users that sometimes used it, both in the New England universities and colleges and at MIT, and the few international users that were coming on over the teletype system. And they had something that was the beginnings of the shell command. We'll talk about that later. CTSS had a one of the first computerized text formatting utilities called runoff. This was an ancestor of, we'll talk about this a little more, of troff or nroff or so on. They had one of the, email. They had a text editor, more or less. I won't say it's like Vi, but the same sort of thing at a more primitive level. And this is the first system to have a password login, at least that I know of. And it really wasn't just a time-sharing system. A time-sharing system was thought of initially as a way to get more out of that expensive CPU. The CPU on a 7090 cost you about $600 an hour. So that 1 minute of CPU time was $10. And on a machine that, like I say, was about as fast as an Intel 8386. And they made a big effort. Any company that had it, and this was in 1960 whatever dollars, and it was quite expensive, and the companies made a great deal of effort to keep that machine busy and get their money's worth out of it. as a time-sharing system, it cracked what had become a bottleneck for writing and debugging programs. How many of you here have ever used the batch process, punch card, Fortran, wait for the line printer output? You really appreciate what time sharing did for them. You know, you were lucky you came in early in the morning so you could get one run in, put in before you went to class or something. And then you came back at lunch and picked up your output, looked at your error message and say, oh, I blew that comma. I'll have to punch another card and put it back in again. And I started out on the IBM 7040, which is kind of a little brother of the 7090 in 1968, doing punch cards, and never want to go back to that. As I mentioned, it had one of the very first, it's stretching the word to say word processing program. It was a text processing package. And it was what led to, called runoff, which led to ROF and INROF. Incidentally, you'll see all the CTSS commands were capitalized because they were working on these ASCII teletypes that had no lowercase characters. You know, or this program, as I said, was the ancestor of a lot of text processing packages that eventually led to the development of word processors. And they had a special editor called typeset that allowed them to put in upper and lower cases characters even on a terminal that didn't have upper and lower case. And runcoms. You may have noticed in Linux and Unix, etc. RC and CSHRC. The RC comes from runcom, and it was basically a file that had a bunch of commands in it. It was the early predecessor of the shell, but it wasn't quite there. You couldn't do substitution that amounted to much. CTS was the first generation of a project that they intended to expand to a much better product. So, and the next generation was Multics, Multiplexed Information and Computing Service. It was designed to be a computer utility in the sense that they were thinking, every city should have their own computer that people could log in, and it should be up 24 hours, 7 days a week, never shut down, and it had a number of other ambitious goals we'll talk about a little bit. At this time, operating systems development was progressing at a fast pace. And there was a whole laundry list of great ideas or not so great ideas, they later found out in some cases, and things that they wanted to do. They were talking about a single level store, which we'll talk about a little more. Dynamic linking and computer security. They wanted a secure system, one that you could trust your files to, and your only copy of files, and one that you didn't have to worry about people getting access to. There were several outfits involved in developing Multics. We'll talk about that more. And there, like I said, there were a lot of new ideas being tried and talked about, and they had a real laundry list of things that they thought they might do with it. And despite what you'll see in some textbooks, particularly Unix, they'll say things like Multics was a failure, and Bell Labs withdrew, which they did, and they'll say things like Ken Thompson wrote a replacement for Multics in a month on a PDP-7. Well, he did write a replacement for compatible time-sharing system, and it took him many years and many versions to do it. But you quite frankly see on the internet things that, like, say, Multics was a failure and that sort of thing. But it was late. Imagine that, a big software project being late. There were actually 3 outfits in it. General Electric Company, which won the hardware bid. They put out a bid for hardware. And the Bell Telephone Labs, which was in it from 65 to 69. And Project Mac of MIT, which was a big bunch of DARPA money or ARPA money. Something happened in 1957. The Russians launched Sputnik, and suddenly the U.S. woke up and said, "We better get on the ball on technology." And ARPA was set up, and it had money and was looking for places to dispense it where great technology could be supported. And MIT was a logical place, and they got a lot of money through the ARPANET, at least for that time. You know, $2 million was real money in 1963 or 4. GE won the hardware bid. They proposed a modified GE 35. 35 was a competitor to the 7094, the follow-on to the 7090, and it had essentially the same word size and very similar structure. In fact, the channels on the GE 635 were essentially the same as the IBM 7090 channels. And GE said, well, we'll make a GE 645. We can easily develop a virtual memory paging unit and, you know, deliver it in a year or so. And, well, it took them a lot longer. Well, I think it was actually that, and I just did a slide forward. It was actually because they were copying a design developed at the Institute of Advanced Studies that started out with an 18-bit word. And they decided that they needed longer words for floating point. So they doubled the size of the 18-bit words. There were, at the same time, a few computers with 32-bit words, but 36-bit words were the norm up until the IBM 360, pretty much. I mean, there were DEC equipment machines with 8-bit words and 12-bit words and 18-bit words. It seems strange to me. It would seem like a Power 2 would be really logical, but for whatever reason, in this time period from roughly 1951 to roughly 1966, 36-bit words were at least the high-end computers used them.
Time around 1968 or maybe 70, CDC, Control Data Corporation, had a 60-bit computer. I know that was, I actually used one in my first job.
I used one remotely, and I think the 60-bit words were great for double precision floating point. That's why the CDCs, they had it set up to do it in parallel, and they could get quite a bit of speed by using that 60-bit, you know, and the architecture paralleled the as much work as they could on that 60-bit, and it was great for double precision floating point. All right. Well, I was going to say BTL, Bell Telephone Labs withdrew from Multics after in 1969, April of 1969. The hardware was late. The software, big software project was late. Surprise, surprise. And they were running about 2 years late. And Telephone Labs just sort of gave up. They had a multi-million-dollar computer sitting there, and they had no software to run on it. And they said, so in April of '69, they withdrew, and this resulted in Ken Thompson not having any, access to compatible time sharing system, except for friends or something letting them on, which was the best software and programming development debugging environment in existence. And he really wanted to have a good software environment since he'd gotten used to it. So he wrote the first Unix system on a PDP-7 that was not being utilized. He kept after his management to buy a nice computer mainframe, and they said, no, we're not going down that route again, and didn't do it. In early 1969, just about the time Bell withdrew, Multics became self-supporting. That is, they could do work on the Multics to develop Multics, which meant they were starting to move off compatible time-sharing system, but they still used it a lot. And by November, they were supporting 20 users at a time, and it had gone into production mid-October of 1969 at MIT. And it was still buggy and slower than desired. One of the things, this is what second generation Multics hardware that was made by Honeywell. Honeywell bought GE's computer division, which was probably a bad decision on their part, but we'll get into that later. This is the central processing unit in the center, right there. And the doors were open because when the idle process was on, it ran these lights right here in a pattern. And you could look over in the machine, oh, it's idle. We could do something more with it, start another process, whatever. And this is the memory process, the system control unit and memory system right in here. Similar flashing lights, but at least in my shop, that we didn't leave that door open. But you notice there's here, these are the system boards. Oh, let me go back. Right there. They're about 24 inches square, and they're, I don't know what they're 30 or so stacked one above each other, and there's a wire wrap back plane on the back, and just a maze of wires running from the back edges, up at the wire wrap pins that are on this back plane. And so this was before integrated circuits. And so this was done in old TTL. And, a lot of these boards are different things, such as the paging unit. Probably, I think those were. And then there's, a bunch of boards, 3, 4, 5, that are in the floating point processor, and the rest is just the normal CPU. And here is the kind of console. This is actually an IBM Selectric type ball machine. The electric version of the IBM Selectric. And in the back, here's some of the peripherals. I think this is the communications processor. My shop had a different processor. So one of the features of Multics, one of the first, is a hierarchical file system. the business that we're very used to of having a root and directories under it and directories under that and going down, you know, maybe not to infinity, but ridiculously far. And the file names were not limited to length. You could have multiple names for a director with symbolic links, symlinks. And before this, you know, you just had a list of files on that disk or that person's directory. And, you know, it seems hard to imagine that. Sorry. That was one of the laundry list of features that somebody thought of, and one that they got to work. And this was one of the two features that went into from Multics that went into the initial version of Unix. The other was the shell. Multics had a shell, not exactly like the Unix shell, but a shell that could, you know, you could use. This is a comparison of some of the commands on Unix and therefore pretty much Linux and Multics and the compatible time sharing system. A lot of things related to directory traversal are not there in CTSS. And mail, capital letters, because you only had uppercase in CTS, and so on. And Multics had a command substitution. It's a little bit different than the Unix, but you know, it's pretty much the same thing. It allowed you to do the same sort of thing. How are we? 436. So we're eventually all good things come to an end. Honeywell was a kind of disorganized company. They had 4 computer lines. They weren't very compatible with each other. They didn't have enough customer base to support 4 computer lines. They got advised by outside consultants and by the internal people that the only viable long-term product they had was Multics, but they were making more money on some of the others. And they were doing the, we can't put any research money out this quarter because it would impact the bottom line this quarter. We'll do it next quarter or next year. And they never did it. And they had siloed, you know, each of the 4 product lines were siloed. And, you know, whoever was in favor with the upper management got the most money. And whichever outfit could argue we're making the most profit for you or we're making the better return on investment. And they never put the money in Multics. Multics also had a problem in that the hardware was asynchronous. If you haven't delved into digital work, you may not recognize what asynchronous meant. But instead of the computer having a clock, it did have a clock, but it didn't, 4 gigahertz or 200 megahertz or something. Most of the instructions, when they ended, they automatically triggered the next instruction. They didn't wait for the next clock. This made the hardware faster initially, but it was much, much harder to design, and they didn't have the design tools like they have now. So this meant that making a new CPU or a new version of it was very costly. And twice Honeywell made designs and got it running in the lab and said, oh, it's going to take too much development to make a faster processor. We'll do it later whenever. And they never did. They did introduce the second generation processors, like I showed you, which were quite a bit faster by just having a lot of cache. They did not really speed up the processors. They did, in fact, speed up a little bit of the floating point, but that was about it. And they just finally realized that they couldn't make it in the computer business. And they had an exit plan. They had a part ownership of a French computer company, and the French and government decided they wanted their own computer company, and basically they bought out Honeywell's share of the French computer company, and Honeywell offloaded their whole computer company to the French company, which is what was called Bull, and it consented for a few years. It go back. And so that's why Multics died. Not that it was a failure. In fact, it was continued development through 1980, roughly 9. The last software release was in 1992. And the last Multics system shut down in 2000. There are actually two systems shut down. One was at the NSA, National Security Agency, and one was in the Canadian Department of Defense. Let's see. Multics had a further influence on Linux via the Intel 8386, which I said was one of the reasons that Linus developed Linux. Is he wanted to play with the Intel 8386 paged architecture. Some of the architectural innovations of Multics, like rings, the 8386 had 4, Multics had 8, and they really didn't need 8. I don't think they ever used more than 6. And they had a segmented page memory. As you know, Intel's segmented memory was kind of a disaster. It was not something that you really wanted to program in assembler language. That got into the Intel 8386, and really when they were looking at trying to make something much better than the 8286, which was not a very wonderful machine microprocessor, they looked around and lifted some features from the Multics hardware. In summary, the roots of Linux were a kind of mixed bag. They had a very slight influence from Minix. Minix was the initial development environment that Linus used, but there very little of that ever got into Linux. And when Linus started, Unix was already 22 years old and had added some features from Multics, had added a lot of features, as we saw, from CTSS, and had come up with a bunch of its own features in the 22 years. And in the 34 years since Linux developed or started Linux, more features from Multics and other in homegrown in Unix have been added to Unix, and most of those have ended up in Linux. That's the end for me. We're 4:43, so I'm willing to take questions.
I do have one. Do you know if Ritchie and Thompson wound up black boxing Unix from Multics in much the same way that Linus did from Unix? or did they have some of the original code to work with?
They had access, I think, to the original code. I mean, they certainly wrote some of the original code in Multics. I'm not exactly sure which features. In fact, there were 25 people from Bell Telephone Labs that were working on Multics. So there was a lot of knowledge of the internals. And Multics, when they designed it, was really probably the beginnings of modern software engineering. While they were waiting for the hardware, they wrote a Multics programmer's manual, and it was 4 feet of 3-ring binders, and they did a pretty good job of paper planning it. One of the things I didn't mention was Multics was written in a high-level language. The high-level language they chose was PL1. Very few of you probably have done much with PL1, but at the time, it was a hot language. IBM had decided they wanted one language to rule them all. They put the features of COBOL, the features of Fortran, and some features from Algol, and they put it in this programming language 1. And they never really fully implemented. They have a design document on PL1, and they made compilers through the years, but they never really fully implemented PL1. The PL1 on Multics was actually more completely implemented than the IBM PL1 compilers, and they had a very strong motive in making a good PL1 compiler, because they sped up, every time they sped up the code emitted by the PL1 compiler, they got better code and code that took less memory. They recompiled the Multics, and they got a faster and smaller Multics. So they had to put a lot of effort in getting a good PL1 compiler.
The VAX, Digital's VAX PL1 compiler was pretty good too. We used that at the university where I went to school.
I never used the PL1 on the VAX. In fact, I didn't know that it had one. I did use a VAX.
Yeah, we taught CS1 on PL1 on the VAX.
Well, that's an interesting thing. Did you like it?
I did. I learned PL1 when I was an undergrad, and then when I was in grad school, I helped teach it. So it was fun.
Yeah. Another question? Well, we're 4:47. Oh, all right.
I was just curious what you know about how CTSS was developed. Was it in a high-level language, or?
No, it was almost all in 7090 assembler. There was another language. I mean, Fortran was the main language of the 7090, and that's what people cranked out. There was also Lisp on the 7090, and there was something called Michigan Algorithmic Decoder, which was a kind of a cut-down version of Algol developed at the University of Michigan. They had a 7090 class machine, and there were a very few, like 2 routines in CTSS that were written in MAD. So maybe the idea first came in CTSS, but it was basically all this 7090 assembler, which, well, I looked at it, but I looked at the 7040 assembler, which is very similar, and never did anything with it. Well, great. And I may mention, so I don't have a slide here of it, There is a SimH, there's a simulator that'll run on Intel architecture machines that you can run Multics under. DPS SimH, Multics SimH, and it's out on the net. It's easy to find. And the source code was released in the public domain in early 2000s, like 2006. They had to twist Bull's arm pretty hard, and it's available from a site on MIT if you want to look at the Multics code. And I have reams of printout from the days I was system amending, which I've been unwilling to throw away. Any other questions? I guess we're officially done. It's 4:49.